Okay, let's start. Welcome everybody to today's lesson on security issues in swarm robotics. My name is Volker Strobel and I've started to study security issues in swarm robotics in 2016. Back then I started as a PhD student at Iridia here at ULB, and in the last 8 or 9 years I've focused on that and I tried to address these security issues using blockchain technology. So today's lecture will also have a focus on blockchain technology. This is why you see an illustration here of a blockchain. Now, before we delve deeper into the topic, I would like to start with a short teaser. It's a clip from the Netflix show Black Mirror. The episode is called Hated in the Nation. So it's from season 3, episode 6. I will now play it.
Jesus. I didn't expect to find myself living in the future.
And this is how we at Iridia and also at other swarm robotics labs envision the future of swarm robotics. So we have a large number of robots. They are controlled in a fully decentralized way. And whenever there are any disturbances or disruptions, they just self-organize themselves back to their original structure. Of course, we are not there yet because this is a futuristic vision, but I think it was a nice mainstream example of how swarm robotics is supposed to work. Now, short spoiler alert, the show is called Black Mirror, so of course everything goes wrong there. So if you still want to watch the show in the next minute, I will spoil it a little bit. So let's go. So of course, everything goes wrong in the show. So these robots, this robot swarm was supposed to be used as a replacement for honeybees. In the show, the natural honeybees died out and they developed these artificial bees to fertilize flowers. But a hacker was able to gain control over the swarm and completely go against its original intention. That's why I put security here in boldface today, and that's why we are very interested in preventing such very dangerous situations. My talk today is structured into 3 parts. So first of all, I want to talk about the shortcomings of classical approaches in swarm robotics. Why is it not enough to just assume that they are fault tolerant, as it's often said? Then, in the second part, I want to introduce blockchain technology because we use blockchain technology to address the shortcomings of the classical approaches. And then in the third part, I will actually discuss and present you how we use blockchain technology to securely coordinate robot swarms. Now, let's start with the first part. So, I think you know about the fundamentals of swarm robotics. So it's a field inspired by swarm intelligence. There is no central control unit. Instead, the behavior of the swarm is a result of the local interactions between each member of the swarm. So it's a self-organized entity that is decentralized. It's not centrally controlled. It's instead based on the control software of each individual robot. Why is it not centrally controlled? Well, because of several reasons. First of all, decentralization prevents a single point of failure. So imagine you have a ground station and you want to control a swarm of drones. Well, if the ground station breaks down, the entire swarm breaks down. It also leads to less communication overhead. Let's assume you have a swarm of 1,000 drones. If they all need to communicate with the ground station to receive control commands, this would not be possible. It would lead to a communication bottleneck, and there would then also be no scalability. You could not use 1,000 drones with a single control station. And furthermore, decentralization enables remote deployments. So imagine that you want to deploy a robot swarm in a cave or somewhere underwater or on a different planet. Maybe it's not even possible to install such a central control unit, but if you have a swarm and you adhere to the decentralization, you can just deploy your robot swarm anywhere. So we don't want central control. Now, how do we imagine to use robot swarms? I think a nice example could be some search and rescue scenario, or in general, some catastrophes that happen anywhere in the world. Maybe there's a fire burning on an oil platform. Then we could send a robot swarm to go there and maybe find persons and bring them back home or bring them to the hospital so we can rescue them. Another option might be to, if in such a case there's probably an oil spill forming in the sea, we can use a robot swarm to constrain this oil spill and make sure that it does not lead to the release of the oil everywhere in the sea or in the ocean. And another option might be that we want to send a robot swarm there to sense the toxins that are released into the air. For example, this robot here might believe there are 5 parts per million of a certain toxin, this one here 13, and so on. And this is really also a scenario that we will discuss further today. So in such a situation, if there's a fire, well, what happens if one of these robots maybe crashes, falls down off the sky? Well, actually not so much happens because we have this property of fault tolerance by redundancy in robot swarms. We just use so many robots that it doesn't even matter if some of the robots break down. However, what happens if they don't completely fail down or break down, if they just fail partially? And that's maybe a bit counterintuitive, but actually a partial failure is more severe than a complete failure, because a partial failure can also infect other robots in a swarm. So let's say this robot here says that there are 0 parts per million of this toxin in the air. So the air is completely clean. Well, then other robots might just take over this estimate, and this misleading estimate would spread like a virus in the swarm and would give completely wrong results with potentially dangerous outcomes. And we really want to prevent such a situation. And in order to study such situations, we introduced the notion of Byzantine robots. And Byzantine robots is just an umbrella term for robots that show faulty or malicious behavior. So whenever there is a clash between the intended behavior of a robot and the actual behavior, like in this scenario with the 13 parts per million and the 0 parts per million, whenever we have this clash, we call such a robot a Byzantine robot or a bad robot. And there can be many different cases why it becomes a Byzantine robot. So in this scenario that I just showed you, well, maybe some smoke blocks the sensors of a robot, or maybe it loses the connection to GPS. Maybe the programmer just forgot to update the code, or more severe, and as we've seen in the Netflix show, maybe a hacker introduced a malicious robot, or it hacked an existing robot. So there is an infinite number of things that could go wrong, and we want to prevent these bad situations. And again, we call these robots Byzantine robots. This is an important term for the rest of my talk, so please remember it. Now, we have studied such a scenario in simulation and also in our lab. So we don't have a fire, we don't have drones, but this is a proxy to study such a situation. So here the robot's task is to determine the fraction of white tiles in this environment. But the white tiles could be the toxins that we've just seen in the example. And in our setup, the robots just move above the floor. They have ground sensors. They locally estimate how many white tiles they see, which fraction of white tiles they see. And whenever they are close to other robots, they exchange their information and try to reach a consensus. How do they reach a consensus? Well, there are different consensus protocols. We studied a protocol called the Byzantine Linear Approximate Consensus Protocol. And it's a relatively simple algorithm. So this algorithm just calculates a weighted sum between a robot's own estimate and its neighbors. So whenever a robot updates its estimate, shown here, h I of t, so I is the robot, well, it takes its own sensor readings that it has sensed so far, and it also takes into account the values that were disseminated by the neighbors it encountered in the last time steps. So this n here is the set of neighbors of a robot. And because it's Byzantine linear approximate consensus, it takes into account these Byzantine robots, and it does so by discarding the largest and smallest values that it has received. And we can see that this algorithm is able to achieve the goal. So here on the x-axis, we see the actual percentage of white tiles. So we used different setups. We varied the percentage of white tiles in this scenario from 0 to 100%. And on the y-axis, we see the absolute error of the robot. So we just randomly picked a robot at the end of a run, and we looked, what did this robot say? How many white tiles are there? And if the robot said there are 40% white tiles, but actually there were 70% white tiles, then the absolute error would have been 30%. But we can see the absolute error is much lower. It's almost always below 5%. So the algorithm works really well, and it is able to achieve its goal. And what I also would like to say is we just picked one robot randomly because we assume that they have reached a consensus. And if there is a consensus about something, it should be enough to just pick one or a few robots and not look at the values of every robot in the swarm, because otherwise you don't need a consensus protocol anymore. You basically then would aggregate the values at the end of a run, and you would have an aggregation of an aggregation. It's not the right way. Instead, you just look at one or a few robots. So this seems to work well. However, what happens if a robot swarm keeps a constant estimate of 0% white tiles? What happens if we actually have a Byzantine robot in the swarm and it does not update its own estimate. Well, there are two potential outcomes then. If you wait until all robots have approximately the same value, then they will either all converge to 0% white tiles. So they will all converge to the estimate that is held by this one robot, because you would only stop the experiment once they have all agreed on the same value. But this robot is very stubborn, so it will never change its value. Or what actually happens if you run the experiment, you would wait forever, for an infinite time. So if you want to wait until all robots have the same value, well, they would always influence each other, but they would never really converge to this 0% white tiles. So the outcome is very undesirable. And we can really see here one of such Byzantine robots is already sufficient to destroy the system. Now you could say, okay, we don't want to wait until they all have the same value. We just wait for example, 1000 seconds. Sorry. Well, also then we see that if we again randomly select one of the robots in the swarm, as soon as we have a few of these robots, the error grows very quickly. So if 3 out of 20 robots in the swarm always say there are 0% white tiles, well, then the absolute error is already at 25%. So this estimate of the swarm is useless. And the values up here show that the absolute error can actually also be 75% in case you accidentally picked a Byzantine robot, because the Byzantine robot would say 0% white tiles. But in this setup now, we fixed it to 75% white tiles. But if you pick this Byzantine robot and you are unlucky, then yeah, it says 0% and the estimate is completely off. So we can see, even though this classical consensus protocol is called Byzantine linear approximate consensus protocol, in fact, it's not really resilient to Byzantine robots. And that's not all. It can get even worse. What if a robot performs a Sybil attack? So this is a problem in general, both in centralized and also decentralized systems. If there is no limiting factor, robots can just create new IDs on the fly. So you don't know if a robot controls several identities. It's Sybil attacks are a general problem in computer science. And as I said, can also happen in centralized system. Let's say there is a website, a poker website, and it gives you a sign-up bonus of 50 euros. Well, because it's online and no one maybe checks your identity, you could sign up with one email, then you sign up with another email address and so on, and you would always get another 50 euros. But a centralized entity can, of course, then establish limiting factors, like they could ask for your phone number, they could ask for your address, they could ask for your identity documents. So there are ways to perform or to prevent Sybil attacks in centralized systems. However, in a decentralized system like a robot swarm, this is much harder because yeah, you don't know which robots are part of the swarm. You don't know if one robot says in one moment, I'm robot 1, and the next moment, the same robot says, I'm robot 2. So one robot can control many different identities, and this then completely destroys the system. So we see here, if one of the robots performs a Sybil attack, the absolute error in percent is already at 40%. So to summarize, to reach a consensus, One Byzantine robot is often stronger than the rest of the swarm. Even if you would have 1,000 robots here, if you have one very malicious robot, it could already break down the system. This brings me to blockchain technology. So, to give you an overview, blockchain makes it possible to maintain a trustworthy database in a peer-to-peer network. So, whenever you don't fully trust other nodes in a network, but you want to trust the information that is stored in the network, then it might be a good idea to use blockchain technology. And we exploited this feature by replacing these computers with robots. So we established a peer-to-peer network of robots that maintain a blockchain network. Now I will, the next maybe 30 to 40 minutes, I will talk a lot about general properties of blockchain technology, because I think it's important to know. It's important to know for this research, but also in general. I think it's interesting technology. It's good to know what it does, and it's made up of several components like cryptography, digital signatures, consensus protocols that are important building blocks of computer science. So, in general, if you want to send money from one person to another person, you do this via a bank or via the government. So you would either have cash, coins, and notes, but these are issued by the government, or you would make a money transfer via your bank. So this is the classical way of sending money from Alice to Bob. And this whole idea of blockchain technology was to get rid of the bank, to get rid of the government, and to create a digital currency that does not require centralized control like banks or governments. So suddenly Alice could directly send money to Bob. So this is why some people call Bitcoin digital gold, because you don't rely on a bank or on a government. It's closer to gold than to the classical money we are using. So why would you want to remove the bank in the first place? And I think this is an important question that some people maybe often overlook if they jump on the hype of blockchain technology and Bitcoin and Ethereum and so on. You should have a good rationale to actually remove the bank. Well, a first consideration could be that you want to save costs. So in general, just sending money within Belgium from A to B is as a private customer free of charge. But if you want to send money abroad, maybe to the United States or to a very remote country, it can already involve huge costs. And also, if you're not a private person, but if you are a company, you would actually have to pay your bank for handling your money. So this is a first good reason, I think, because especially in the before they introduced in Europe SEPA transfers, it could have been quite expensive to send money from A to B. And I still think if you want to send money nowadays to several countries, there could be huge costs if you use your traditional bank. Then a next good consideration could be that you want to speed up the transaction. So also here, traditionally, it took several days to if you made a money transfer using your bank. But maybe you want to be much faster. Maybe you want to transfer the money almost instantaneously. This could be a reason to use blockchain technology. Another reason could be that you don't trust your bank. This also, again, depends on the country, but you never know. Maybe the bank runs away with your money, or maybe it's a small anecdote. Even here in Belgium, I think last year I tried to transfer my portfolio from one bank to another, but the bank was just ignoring my instructions. So it did not transfer my portfolio. Of course, then I could have gone to a lawyer and to court and everything and could have complained about that, but it would have been a huge hassle. So even in Belgium, it could be a reason that you don't fully trust your bank and you would like to be in charge yourself to handle your money. Another big reason for several people is that they want to stay anonymous. Banks have this know your customer principle, but sometimes you want to be anonymous, maybe for political reasons. Maybe it's not allowed in your country to buy certain things. Maybe you don't want that the government knows everything about what you buy and what not. But this thing here has also been exploited by criminals. So Bitcoin was involved in and is still involved in a lot of criminal activities, like dealing drugs or weapons online. Another reason could be that your bank is simply not reachable. Maybe the website is down and you're desperately trying to send some money to a person, but it doesn't work. You might have ideological reasons. You might believe in decentralization of the world, and you don't want that a single entity is responsible for handling your money. And maybe you also don't want that the government is just creating money out of thin air. Let's say what many central banks do nowadays, that they can just print an almost infinite amount of money. Then this is similar to what I said about the anonymity. Maybe there's some censorship and you are simply not given access to your money, and because the bank or the government blocked your accounts. Another thing could be that you want to have a non-reversible transaction. So in general, if you pay by PayPal or using your credit card, I think if you somehow see some suspicious activity, or I think you can complain at the companies and you can reverse a transaction. But sometimes maybe the recipient of the money wants to be very sure that they really received the money and that the person who paid has no means of reversing a transaction. Another reason could be micropayments. Maybe your bank would have huge fees if you want to have many hundreds of thousands of transactions with just a couple of cents. Maybe you want to use it in a computer game, and whenever you win some money, it immediately comes to your account. And this one here is also a big thing that we will use today, is payments that are triggered by events. So maybe you want to program your money. Maybe you want to say only if a certain event happens, like only if the weather in Belgium drops below 20 degrees Celsius, then pay some money to a certain person. So overall, maybe you want to be more flexible and not only rely on your bank. And I think if you deeply think about it, you could come up with many more reasons why you don't want to always rely on a bank. So it could be a good idea to develop such a peer-to-peer financial system. However, it poses many challenges. Like, how do you validate transactions? How do you make sure that if you see a transaction, that the person who is named in that transaction really created that transaction? How do you make sure that someone only spends money they really have? How do you create new money? So who is the creator of the money? How can you make sure that no one manipulates the system and that no one just gives themselves some extra money? How could you make sure that the same coin or same token that you have is not sent simultaneously to different persons? So overall, it's really how do you reach a consensus on who owns what in a decentralized system? And the person who solved that issue for the first time was Satoshi Nakamoto. And Satoshi Nakamoto developed Bitcoin and wrote a white paper about the implementation of Bitcoin. So this person did that in 2008. Then in 2009, Bitcoin went public. And now in the last 16 years, it has really seen huge success and huge growth. So we had Bitcoin, who got rid of the bank and the government. Now, what is a blockchain exactly? In general, it's just a database. And it's a database that consists of a chain of blocks, of linked blocks. That's why it's called a blockchain. And each block contains a snapshot of the current data. The data could be, for example, send 5 Bitcoins from Alice to Bob. And then every 10 minutes, for example, a new block would be created that has also a link to the previous block. So you could have this sequence of blocks that created the blockchain database. Now, people often ask, but where is the blockchain stored? Where does it exist? Well, on each participant's computer. So every participant keeps a local copy of the blockchain in such a peer-to-peer network. And as I said, where does the data come from? Well, the data is a list of transactions. And a transaction would be a certain number of Bitcoins that are sent from A to B. So if Alice, for example, wants to send 5 Bitcoins to Bob, she would create a transaction using her Bitcoin software. Then this transaction would be published in the blockchain network. It would be propagated through the network and it would travel to other computers. Then at some point, a computer would create a new block and would put this transaction as part of the block. And then this block would be disseminated. At some point, it would reach Bob, and Bob sees, okay, I really received 5 Bitcoins from Alice. And Bob would only trust this transaction if it's part of a block. So only then it can be considered trustworthy. Now, this sounds nice and well. However, how can you make sure that it was really Alice who sent the money and that it was not, for example, Bob himself? Maybe Bob tried to access the bitcoins from Alice and created a transaction that sent Alice's bitcoin to him. Well, for that, the Bitcoin protocol uses digital signatures. So every computer in a network would check the signature and would check if the signature really comes from Alice. Now, how does a digital signature look like? Well, digital signatures are based on public key cryptography. And with digital signatures, you can sign documents. And it's the same principle as with signatures in the off-chain, in our classical world. When you make a signature to, if you add a signature to a document, you show that it was really created by you. And with digital signatures, this mechanism is different because it's more complicated. You would have a pair of a private key and a public key. And you can derive the public key from the private key, but you cannot derive the public key from the private key, but you cannot derive the private key from the public key. So it's this one-way street here. So it means you can distribute your public key everywhere in the world. This is your public identity, but you should never reveal your private key, your password, let's say. And now with digital signatures, there are two important functions, and these are implemented by software that use digital signatures. So one function is the sign function. Whenever you write a document or you write a text, you write an email, whatever you want to digitally sign, it could also be software. For example, you write some software, you would sign it using the document and your private key, and the result of this function would be a signature. Now you can publish this document together with the signature anywhere, for example, in a forum or in an email, any channel, whether it's trusted or not. But everyone who knows your public key can then verify that this document was really created by you. And this would be done using the verify function, which has as an input the document itself, the public key of the creator of the document, and the signature of the creator. And then this verify function would just say true or false. Was the document really created by the person who controls this public key? And if this is still a bit unclear, I would like to show you a short practical example of how to use digital signatures. So now I will just open two terminal windows to show you how you can digitally sign documents. So let's say this is me, green is me, and blue is you. And I want to send you some document, and I want to prove that this document was really created by me. So to do so, first of all, I would need to create a private public key pair. I've already done it, but I still show you how to do so. So for this, I will use this software called GPG. And I think it comes by default on many Linux based systems. So it's the Open PGP encryption and signing tool. Okay, so the first step, as I said, would be to generate this private public key pair. And this is done with this command. And then it would just go through a couple of questions. So it would ask you what kind of key would you like to create. So we can just here go with the default. How many bits should it have? How long should it be valid? You would specify your real name, your email address, and then maybe there are a couple of other questions, and then you would already have this private public key pair. Now, after this is done, you would distribute your public key and your public key only. You should never reveal your private key. So whenever you and me, whenever we meet at maybe in person, so that we can be really sure that this public key belongs to me, we would exchange our public keys. So this example is only important that I give you my public key. And this would be done like this with this command. So I just say that I want to export my public key into the file volker.gpg. And this command here, armor, just says that it should be done in plain text and not as a binary file. And I did it because I want to demonstrate it, and it's easier to understand if it's plain text. So now we can look at my public key, and it just looks like that. It's really a long string. Now I would take this public key and somehow give it to you. And you would then take it and import it onto your computer. And this would be done like that. Now, whenever I want to send a message, I can sign it. So let's create a message. Say, hello, Swarm Intelligence. And I store this message in the file message.txt. Now I sign it. Need to enter my passphrase from the private public key pair that I created earlier. And now we have a signed message. This one. So the message contains both the original message, hello Swarm Intelligence, and the signature. Now I would send you this message. I can post it as it is like this in a forum, or I can send it to you by email or whatever we want. And you can then verify that this message, hello Swarm Intelligence, was really created by me. And you would do so based on the public key that we have exchanged earlier. So you would then just take this message and use GPG verify, and you would see it's indeed a good signature from me. And what happens if we manipulate the message? So let's say when it was transferred to you on the way, there was an attack and someone tampered with it, someone manipulated. So let's just do it. So let's say instead of hello swarm intelligence, we say bye swarm intelligence. If we verify the message now, well, it says it's a bad signature. And there would be no way to create a valid signature after you tampered with the message. The only way would be to obtain my private key, because only with that private key you can actually create valid signatures. All right, now back to the slides. We now solved the first problem of blockchain technology. How do you ensure that it was really Alice who created this transaction, sent 5 Bitcoins from Alice to Bob? Now, the next important question is, how do you ensure that everyone in the network has the same version of the blockchain? Because if they all locally store the blockchain, they might have different versions or different forks, how they are called in blockchain terminology. And another important question is, how do you actually add new blocks to the blockchain that contain these transactions, that contain the transaction Alice wants to send 5 Bitcoin to Bob? Well, in order to do so, you need a consensus protocol to reach a consensus on the information that is stored in the network. And in Bitcoin and in blockchain technology, the longest blockchain is accepted as the true blockchain, or in more technical terms, the blockchain that contains the highest amount of work. So where it was the most difficult to create that blockchain. So in this example here, all of the nodes would say this blockchain here is the true and factual blockchain, because these ones here only have 2 blocks. This one has only 1 block, and they have a lower amount of work in them. So what is work exactly? Work is the number of calculated hashes. So whenever we talk of mining in blockchain, we are talking of calculating hashes. I guess you've heard of hash functions, but just as a short recap, a hash function is any function that can be used to map data of arbitrary size to data of fixed size. So this could be here a very long string, for example. It could be some piece of software, it could be an email or whatever. And then you would just map it to some data of fixed size that maybe always has 100 characters. And you especially want to make sure that if you use different values of x, you don't it doesn't lead to the same value of y. So you don't want to have a collision here. Then there is a special set of hash functions that are called cryptographic hash functions. And these are non-reversible hash functions. So whenever someone gives you y, it's very hard to find x. So you cannot find out which data was hashed in order to lead to y. And this property here is used in the Bitcoin mining puzzle, in this proof of work. So proof of work or mining is the activity of finding a solution to a mathematical puzzle that can only be solved by brute force. And you would brute force this hash value. So you want to make sure that it starts with a predefined number of zeros. So as input to the hash function, you would take the contents of a preliminary blockchain block, and then you would additionally add a nonce. And a nonce is just an arbitrary number, and in each iteration, you just increase this nonce by 1, and you do that until the contents of the block and the nonce, when hashed together, lead to a hash that starts with a predefined number of zeros. And I will show you in a moment how this looks like in practice if it's still a bit cryptic to you now at the moment. But here is again an illustration of that. So as I said, the blockchain is built of a list of blocks. Each block contains data. The data are the transactions, like Alice wants to send 5 bitcoins to Bob. Now, whenever you want to mine a block, you would take the data, you would take the hash value of a previous block, and you would take an arbitrary nonce, and you put that into a hash function. And you try it with a certain nonce, then maybe you see that the resulting hash does not start with that number of zeros, then you would just try it with another nonce, and so on. And there's no way of speeding up this process because we are using a cryptographic hash function. So you cannot say that you start with the hash that maybe starts with a certain number of zeros, and then you find out which nonce you would need to use to lead to that hash. It's a bit complicated to explain, but I think if I show you an example, it becomes much clearer. So I wrote a very simple example in Python. So this is really the whole script, and it just contains two functions. One is this SHA-256. It's a hash function, a cryptographic hash function. And this other function is mine, which just automizes this process of finding the right nonce value. So I will now open that script. Okay, so we can see here now that the difficulty is set to 0, 0. So the hash that we want to have should start with at least 2 zeros. Now, as a first step, I just want to show you how hashing looks like. And as I said, you can use an arbitrary input, and it will lead to an output of fixed size. So we can use this function mySHA-256, can, for example, say, again, hello swarm intelligence, and then it would hash this string and would come up with that hash value. And the input could be much longer, but it would still lead to a hash value with the same fixed size. Now, how does mining work? As I said, you would add a nonce value. So here you would add this nonce. So let's say it like that first, and you try different values for the nonce. You would start with 1. And then you would check, does the resulting hash start with 2 zeros? No. And you would do it with 2. Still not. 3, and so on. This is, of course, a very cumbersome process, so you would automate it. So I implemented this function called mine, where you can, and this does exactly the same thing, just automatically. And then it now tried it 738 times, and it found a solution if you use nonce 738. So if we say hello swarm intelligence, and we attach 738. Indeed, the resulting hash starts with 2 zeros. This was, of course, very easy, but we could increase the difficulty of this mining problem and say, okay, maybe the hash should start with 5 zeros. So we can then do it again. We mine hello swarm intelligence, and then it would really work very hard to find the suitable hash. And this is really the algorithm that all the miners in a blockchain network are performing. So if you have seen some picture of a mining farm in blockchain, of a Bitcoin mining farm, they are just executing this function billions of times. And now we can see if it actually finds a suitable hash value, and you can already see that this takes much longer than before. We'll let it run for a couple of more seconds. I think it will find a solution soon. It should be less than 1 million. I think 1 million trials. Let's see. But I can already hear my computer working hard, actually. Yes, now it found a solution. So if we use this as input, 807720, indeed the resulting hash starts with 5 zeros. All right. Now back to the slides. As I said, this is mining. It's just finding the solution to this mathematical puzzle. The mathematical puzzle is just find a solution that leads to a hash with a predefined number of zeros, and you do that by brute force. Why do you do it? Well, you want to reach a consensus on the blockchain that has the highest amount of mining work, the longest chain. So every miner performs this algorithm. And you want to make sure that the blockchain is immutable. Because only blocks that have this work inside them are considered valid blocks. So if you change the content of a block, then if you hash that with the existing nonce, the resulting hash would not start with that required number of zeros anymore. And this really makes the blockchain immutable. So whenever you would change the contents of a block, you would need to rerun this algorithm, and this makes it very hard for a hacker to change the contents of a block. So as long as a hacker does not have more than 50% of the total mining power in the Bitcoin network, they can not change the content of existing blocks. Then you might wonder, yeah, but why are computers wasting so much energy on this stupid problem? Well, it's because mining is a race, and you want to be the first one to find the solution, to find this nonce, because then you get a reward. So you could actually add an additional transaction to your mined block that gives a reward to yourself, to the one who solved this mining puzzle. And that's why there are so many Bitcoin miners. I think currently the reward is 3.125 Bitcoins. The current price of Bitcoin is around 70,000 euros. So if you actually find a solution, you would get Bitcoins worth more than 200,000 euros. And I already quickly touched upon that. So how do you cheat or attack in a Bitcoin network? You would create conflicting transactions. So you would create one transaction that says A pays B 5 Bitcoins. And then you would create another transaction that says A pays A, yourself or themselves, 5 Bitcoin. And the question is, well, which of these two transactions will end up in the blockchain? Only one of them will end up, because the entire protocol ensures that you cannot have conflicting transactions in a blockchain network. So only one of them will end up, but you don't know which one. This is why you should wait for a couple of blocks. So in the beginning, the transaction is just out there in a memory pool of transactions. It's not part of a block yet. And if you remember previously, I've showed you how these transactions disseminate in the network. At some point, someone would put it into a block, would mine it, would perform this proof of work, and would solidify the transaction. And then with each additional block that comes after the block that contains the transaction, it would be more likely that this transaction cannot be undone. Because if you would change this block, all the subsequent blocks would also become invalid. So changing data in a previous block would require an attacker to redo the proof of work of all later blocks. And I think there's a nice online example of how this looks like. Let me see if I've already opened that. Yes, here. So let's say we have this blockchain here, and it contains of 3 blocks. And in the first block, there's a transaction, send 5 Bitcoins from A to B. Of course, I like just write it in plain text. In practice, the transaction will look differently. It will contain the digital signature and so on. But now here, just for the purposes of demonstration, I will write this plain text. So I send 5 Bitcoins from A to B, and I mine that block. And now we can look here what the resulting nonce will be like. So we mine it, and then it will take some time. And at some point, it should come up with a suitable nonce. Maybe I was, yeah, now it found a nonce. It was rather high. But this data hashed with that nonce and that hash of the previous block together lead to that hash that has 4 leading zeros. Now we can say the same here, and we can actually say send 5 Bitcoins from B to C. Again, mine the block. Yeah, this was faster. And then we send 5 Bitcoins from C to D. And we mine the block. And you can always see here that each block contains a link to the previous block via this hash. So this is the hash of the previous block. This is how it is established that this block here is the previous block of this one. So now we have a nice blockchain of 3 blocks. All of these blocks are valid. Everything is fine. But now let's say A wants to cheat and wants to modify the contents of that block here. So instead of sending 5 Bitcoins from A to B, A wants to send 5 Bitcoin to themselves. So Now I changed this, and then if you've seen it, these other blocks now turned red because this is not a valid block now anymore. Because if you take this nonce, this data, and this previous hash, and you hash them all together, the resulting hash does not start with 4 zeros anymore. And this entire process makes it very hard to manipulate any data in the blockchain network. All right, back to the slides. Now, as a short summary, so far we talked about Bitcoin. The main building blocks of Bitcoin are this peer-to-peer network without any centralized control unit. We have a public database, the blockchain ledger, that contains all transactions of all users that have ever been done in the network, by the way. So if you now install your Bitcoin client, you will, and you download the blockchain from your peers, you will get all transactions that have ever been done in Bitcoin. Another important building block are digital signatures. They make sure that the creators of transactions are really in control of the Bitcoins that they send. And there is this consensus protocol based on proof of work, which is called mining. If you perform the proof of work, it's called mining. And now this was a huge revolution, and then people very quickly realized that Bitcoin is just one application that can be built on blockchain technology. So originally in this white paper of Satoshi Nakamoto, it seemed to be that they are one and the same thing, but it's not. Like blockchain technology can be used for many more things. And quite soon after 2009, there were many other altcoins, alternative cryptocurrencies. And they have been used for different purposes. Some will also be meant for sending some digital tokens, digital money from A to B, but maybe with different features. Like I said, in Bitcoin, a new block is only created after every 10 minutes. Maybe an altcoin does so after every minute. And then it could become faster to send some money from A to B, but with some downsides, because if it's faster, it would also lead to more conflicting blockchain versions. Anyways, there are different use cases of these alternative coins. So, for example, instead of sending digital tokens that are worth money, you could also register domain names. And I think this was done in a project called Namecoin, where you could register a URL. And if you did not want it anymore, you could just send it to someone else. Or blockchains could also be used for voting, because you have this ledger, this database, and it can transparently record all of the votes in an election and can then determine who is the winner. And then at some point there came up a project, the one to rule them all. It was Ethereum. And Ethereum really generalized this idea. It said you can use the database for anything you want. So we went from using blockchain technology for financial transactions to using it for arbitrary data to finally also using it for programming code. And this was the big idea of Ethereum. You can run programming code in a decentralized network. So if Bitcoin got rid of the bank, Ethereum, this blockchain 2.0 that was developed in 2015, got rid of the court and of the government by introducing blockchain-based smart contracts. And this is a bit of a misnomer, because in general, a smart contract is neither smart nor a contract, but still, it's called like that, and it can be smart in a contract. But what it is in general is just that it is programming code that is stored on a blockchain and executed by each participant. And the nice thing is that then all of the nodes in the network can reach a consensus on the input and output of these computer programs. And it's in general less complicated than one might think. So a smart contract is really just programming code that can be written in different programming languages. The most common one is Solidity. And the syntax is very close to JavaScript. And here in this example, I've just defined a couple of variables and two functions, one that takes the square root using a certain algorithm, and one that returns the absolute value of the input. Then, in order to store that smart contract on the blockchain to make it available, you would compile it to machine-readable code. Then you take the machine-readable code, put it inside of a transaction, publish it. Then this transaction would be mined by a node in the network. Then it would become permanent. And then each node in the blockchain network would take these instructions and run them on their local virtual machine, the Ethereum virtual machine, as it's called. And this would lead to a certain output. And this whole idea then enabled arbitrary decentralized applications, or dApps, as they are sometimes called. So while Bitcoin only established financial transactions, suddenly we can have arbitrary decentralized applications. We can store arbitrary data on the blockchain and use it as input and output of programs. Now, I copied here a short quote from the Ethereum website. Why do you want to have blockchain-based smart contracts? Well, because it leads to this tamper-proof code that no one can manipulate. And it's without any possibility of downtime, censorship, fraud, or third-party interference. And this can be quite useful in several circumstances. So as a short motivating example, I present here crowdfunding. And in traditional crowdfunding, for example, with Kickstarter, you would have this centralized crowdfunding platform, and then you want to fund a certain project, for example, a smartwatch. And there would be the backers, they would all use their credit card. And if the required amount is reached, let's say 1 million, then there's this all or nothing principle. So if the 1 million is reached, all of the money goes to a project. If there are only 900,000 euros, the project is not funded, and the backers would get their money back. However, there are a couple of problems with that traditional crowdfunding. Well, the main problem is trust. So on the one hand, of course, the project needs trust. Do the people really develop the smart watch in the end, or did they just make empty promises? And the other thing is that the crowdfunding platform needs trust. So after they collected the 1 million, is the money really sent to the project, or do they run away with the money? Then there's the problem of transparency. Like, they might say that they only collected 900,000 euros, while actually they received 1 million, but it's hard to validate that as an average user. And maybe there are potentially high fees. I think Kickstarter takes something between 5 and 10% of the backers' money. So it could be an idea to replace this central crowdfunding platform with a decentralized crowdfunding platform using Ethereum. And in such a decentralized crowdfunding platform, instead of using their credit cards, the users would create transactions that contain a certain amount of Ether. So Ether is the crypto token of Ethereum, the same as or similar to Bitcoin. They would send transactions to a smart contract. This smart contract is the DApp, the decentralized app, and it would have programming logic inside that does the same job as Kickstarter did previously. And this would be completely decentralized, so there is no single point of failure. Once this smart contract is in the blockchain, no one can stop it, no one can run away with the money. So you have a guaranteed execution of the transfer. So you could have the logic inside the smart contract. Once there are at least 1,000 Ether, then send everything to the project. If after a certain time window there's no 1,000 Ether, then all the money goes back to the backers. Then, because in general blockchains are public, there's a lot of transparency. You can really see how many Ether were collected. The smart contract is immutable, so there's no possibility that someone then later manipulate it and maybe say all of the money will be sent to himself. And potentially you might have lower fees and not these 5 to 10% of Kickstarter. So this is why blockchains in general are called trustless. You don't need to trust anyone. You can trust the system, but you don't need to trust any user of the system. Of course, you still need to trust the people that are promising to develop the smartwatch. So you cannot really get rid of this here. This is still something that depends on humans and their promises. Okay, now I think this was a long introduction to blockchain. Now I would like to show you how we actually use it to enable secure coordination of robot swarms. I've already quickly shown you that we just take this peer-to-peer network that is usually maintained by stationary computers, and we use it with robots. And each of the robots is a node in the Ethereum blockchain network. And this network is also independent of the Ethereum main net. So this is really just a private blockchain that is composed of several robots. And here in this video, I will show you a general introduction how blockchain technology can be used and exploited in robot swarms. Let's see if this works. Robot swarms neutralize harmful Byzantine robots using a blockchain-based token economy. The robots use the ground sensors to estimate the fraction of white tiles. For example, this robot believes that the fraction of white tiles is 23%. However, there are Byzantine robots that send wrong estimates, for example, constantly 0%. Each robot is a node in the Ethereum blockchain network that is maintained by the robots. A smart contract enables the robots to store their estimates of white tiles. In order to submit estimates, the robots have to pay crypto tokens. The smart contract collects the estimates and the payments detects the estimates of Byzantine robots and removes them, and distributes the total amount of received crypto tokens only among the non-Byzantine robots. The robots can only exchange blockchain information if they are close to each other. When a robot connects to a nearby robot, it switches on its red LEDs. When a robot sends an estimate to the smart contract, it flashes its green LEDs. When all robots have received the consensus signal from the smart contract, the experiment has finished. When a robot receives the consensus signal, it permanently activates its green LEDs. We test our blockchain-based economy using different swarm sizes and arena sizes, and show that it successfully neutralizes Byzantine robots. In simulation, we further show that the presented approach scales to robot swarms composed of 120 robots. Okay, so in this research, we could demonstrate several important facts. First of all, we could show that it is possible to control a physical robot swarm via smart contracts. And this is an important thing because people were previously very doubtful. They were thinking of these huge blockchain mining farms, then they were thinking of blockchain technology, and they said, okay, it will not be possible to control these small robots using blockchain technology. However, we made some adjustments, like we did use a different consensus protocol based on proof of stake and not proof of work, which is much more lightweight and which enabled us actually to control even these relatively small physical robots. They have approximately this size, and on top of their robot body, they have attached a Raspberry Pi Zero W. And this is also a relatively simple single board computer, but blockchain technology used less than 35% of CPU and RAM of this computer. Then the messages were larger than plain messages traditionally used in robot swarms, but with approximately 160 bytes per message, it was still manageable. So each message, like there are 63% of black or white tiles in the environment, well, we would increase the total storage by 160 bytes. Then we could show that the smart contract that we developed was resistant to different Byzantine faults, like we had some robots that were always sending 0% white tiles. Some robots were drawing their estimates from a random distribution, but our smart contract could neutralize all of these Byzantine robots. And we can see that the results are, in fact, quite good. So if we have 24 robots and 9 of them are Byzantine, in this case are sending an estimate of 0% white tiles, the absolute error is on average below 3%. And this is in contrast to the baseline, where it goes up to 9%. And our baseline was still quite soft, let's say, because we did not perform any simple attacks or similar more severe attacks. And also in terms of the convergence time, it was reasonable, but with a larger number of Byzantine robots, it took a bit longer until they all agreed on the same value of white tiles. And what we could also show is that the economy was the factor that neutralized the Byzantine robots. So the Byzantine robots, they got poorer and poorer. The other robots, the good ones, got richer and richer. So this leads to some potential business applications in the future in the real world using blockchain-enabled robot swarms. Another thing we could demonstrate is that the system is reasonably scalable. We tested different arena sizes, different robot sizes, as shown in the video. And if we executed the experiment for 10 hours using a quite large swarm of 120 robots, well, the blockchain grew to 70 megabyte. This was still quite manageable because the robots that we used in this experiment had this Raspberry Pi, which had an SD card slot, so you could even have an SD card with 1 terabyte or so, and then you could run the experiment for several years. So the battery power would be a much bigger issue than the blockchain storage space. And now that we have established all of these fundamental questions, and we've shown that blockchain can help to secure robot swarms, we are currently trying to see where can we use it. And we have several different research directions for that. For example, how do we ensure that all robot swarms perform the same action at exactly the same time? How can we exploit it to perform simultaneous localization and mapping so that we store the waypoints of SLAM in the blockchain? Or what I present now is how can you implement it to create secure distributed machine learning in robot swarms? Well, how do you implement secure machine learning in robot swarms at all? It's a relatively challenging question. So each of the robots might have collected some data about something. In our example, it's trajectory data of other robots using a camera. But then the question becomes, well, how do you share these large data sets of potentially confidential information? If you record videos, could be that there are also people in these videos and they don't want that the video material is somewhere stored, maybe even publicly. Who trains the model in a robot swarm if there's no central server? And how do you identify poisoning attacks? What if one of the robots is just sending complete rubbish data? Well, what we did is we used federated learning. This is a machine learning technique where each device in the network would actually locally train a machine learning model. And this machine learning model is then aggregated using a blockchain smart contract. So this is, instead of traditionally in federated learning, you have a server that aggregates all of the models. Now we use a smart contract. And we can see that this works very well. And over time, the average loss of this trained model becomes lower and lower. Now, similar to the other research, the question becomes, what if one of the robots tries to poison the global machine learning model and sends misleading weights of the network? Again, we see that one Byzantine robot is sufficient to completely destroy the system if you do not take care, or if you do not make any precautions. So what we did is we implemented outlier detection on the smart contract that could identify these poisoned models. And then we again see, even if we have 7 Byzantines out of 15 robots, the model works very, very well, and the error is decreasing. So to summarize that, how do you implement secure machine learning in robot swarms? First, how do you share large data sets containing confidential information? You do not. You only share the weights. Where do you train the model? Directly on the robot. And how do you identify poisoning attacks? Via outlier detection implemented on a smart contract. So to summarize all of this research and to summarize our original research question. Can blockchain technology secure robot swarms against Byzantine robots? Here, I think we can say, yes, we have seen several supporting results. So we've seen that blockchain technology enables robot swarms to detect inconsistencies in other robots and also to control a robot swarm. So this consistencies or inconsistencies could be data inconsistencies. If one robot just has a different blockchain version or manipulates the data, this blockchain version would get discarded. And if a robot does not perform according to the protocol, this could be identified in a completely decentralized way, and this robot could be neutralized. It could also be used for post-mission identification of misbehaving robots and could lead to some potential sanctions of the owner of the robot. Because the blockchain actually keeps a logbook of all crucial things that happened during a mission. And what we showed already is that the blockchain can also control the robot swarm. It's like a decentralized meta swarm level controller that could, for example, tell one robot search for a victim, another robot approach the victim, and yet another robot rescue the victim. Then we could show that blockchain technology prevents these Sybil attacks by introducing scarcity, by introducing crypto tokens that cannot be created out of thin air. What we are currently looking at is also into open robot swarms, where you implement a DAO, a decentralized autonomous organization, using a smart contract. And such a DAO is a company, basically, whose policies are implemented in a smart contract. And then you could have some decision making by both robots and humans. And the DAO could, for example, decide if a new robot is able to join the swarm, or maybe the DAO says, no, we already have enough robots. Then we have seen that we can create economies among the robots. We have now used it to identify these Byzantine robots. In the future, we can envision other applications. Like a human could say, I need a map of a certain environment. The human would send some crypto tokens to the swarm. The swarm itself could exchange crypto tokens whenever one robot sells a piece of the map to another robot, and then finally return the map to the human. So we could really have in the future an economy that involves humans and robots. So to conclude, what I've showed today is, in order to identify Byzantine robots, you need a secure system. And we found the secure system in blockchain technology. Now that we have a secure system, I believe we can do much more than just identifying Byzantine robots. In all applications where security is relevant, we can see how does blockchain help and how does it enable the robot swarm to stay secure and perform its task. That's it from my side. Thank you for joining today. And if you have any questions, please feel free to ask them now. You can unmute yourself, you can write them in the chat, or if you have any questions later, you can also write me an email to this email address.